Thank you everyone for spending your last session here. Uh, so today I'll be speaking on leveraging digital twins and OpenSearch for personalized customer experiences. My name is Satej and I work at Zalando. I basically work in Berlin, so that's where I'm from. Just a brief disclaimer before I start. So the views, opinions, and ideas expressed in this presentation are solely my own and do not reflect in any personal capacity the stance or perspective of my current or past employers. So starting from here, the very first question is, what is personalization? So when we think about it, personalization happens at many aspects. You visiting a shop and getting a personal preference in terms of what your behavior has been in the past and what you're expecting right now gives a very personalized experience in terms of the feedback which you expect it to. So right now, personalization is somewhat broken today. And some of the reasons has been that we do not have a holistic framework to support this. If you see in different organizations, it's supported through different variety of ways. There is data siloed throughout the organization, so you don't have a holistic 360 view of the customer in terms of what they are doing. So you have to crunch, connect, and bring all those data together. And eventually you have the requirement of GDPR, so you have to eventually pseudonymize your data in order to process customers' data, and you have to also get customers' permission that you are using this in order to help them give more personalized feedback in terms of whatever they're doing. And the fourth is about privacy. So eventually you have California laws and GDPR and all about how do you handle privacy at the same time without exposing all these details. So here, I wanted to talk about two particular aspects as to how do you bring about a digital twin. So first question, how many of you have an idea of to what a digital twin is? Okay, so that's a good start. So for me to bring about the concept of digital twin, so digital twin is basically a digital replica of a physical object, person, system, or process contextualized in a digital version of its environment. To speak about it, if you see in this picture, there's a physical asset which is a kind of a machinery which does its in a physical world. It's a physical existing object. But how about what is the data you have of it in real time in a in an IT system wherever you're working in? What is the real time insight you have of this particular system working on the ground? So let's say when this particular instrument is working, what is the pressure it is undergoing when it's picking up something? What is its relevancy in terms of its past historical? Let's say yesterday it was used for 5 hours, today it has been used for 6 hours. So do you have this realistic data of it? So if you try to use this data, you have a digital version of it. When you think about a digital version, you can represent what is the pressure it is undergoing, what is the speed at which it is going, and all of this data you're capturing through sensors. So there are sensors which are attached to this device, which gives it what is the wind pressure which it is going through, what is the amount of load it is currently holding. So all of this data is being transmitted in a real time to your software systems. So you have a digital version where you can lively see what the current state of the actual physical asset is. So that gives you a digital representation of it. This is what is called a digital twin. Now to explain, and I hope this gives somewhat an idea about what a digital twin is. Now, already there are many real-world use cases about how it is being used. One particular example is Formula One racing, where it's a very highly competitive industry, and given the rising cost, there's always the pressure of, how do you deliver the best performance without spending too much? Because when you're experimenting or trying out on the tracks, you have a limited number of tryouts, and within that you have to test different conditions in different terrains. With that, a physical version cannot do everything. So with that, what happens is teams are collecting a digital version of it, where they are collecting real-time pressure of the tires, the sensitivity, the road terrain, everything in detail. And these are all captured in thousands of millions of events per second. And these are captured in a database, in a software, and you can act on these. So you can think in one aspect is, if you collect all these data, you're having a digital representation of it. The second is you can work on this data real time. So let's say one example is, if you collect data on the tires in particular and you see the condition has been deteriorating in terms of what it was yesterday or day before yesterday, you get a chance for predictive maintenance instead of waiting for the tires to fail and then act on it. So it helps you to act proactively on this. The second case is the football NFL. So there is a very wide use case as to representing how actual athletes are performing on the ground by measuring their muscle elasticity, how fast they're performing, their breathing rate. So all these gives you a digital version of the person who is performing there, which again gives you how they're performing, how you can take some actions on them. Let's say if you're seeing some very different breathing patterns, that gives you an indication that something is wrong with the person. So instead of waiting for them to collapse, which is a very last and action, but let's say in this case you can take a preventative measure and call them off the field. Very similarly, there are different other aspects which helps in maintaining a digital version. Very similarly, what happens is, how can we consider the digital twin of a customer? So when you think about a customer, they go to your shop, it could be a retail store, it could be an e-commerce website. So they go, they shop, they have different preferences. They buy from different designers. Let's say you like kids and shopping category. Someone else likes, let's say, sports category. So you have very digital representation of a person in terms of the choices, their behavior, at what time they shop, maybe during Christmas, or they love shopping. So these are kind of the characteristics of a person. But if we represent it from a digital version, we also can have this data stored somewhere, which can act for us. We can act on this particular data set for our own use cases. So here if you see there's a customer, they are interacting, and these are different channels. These could be your retail shop, for example, and these could be very easily translated to other industries too. But here I will just focus upon the retail industry. So you have an e-commerce website, they shop there. You have a mobile app where they can also shop, and you also have a retail store. So if you consider these three channels in particular right now, customers interact at different times across these devices, giving you all these inputs in a data format. So you're collecting all these through cookies, events, from Google tags, Google Analytics, etc. So you have all these data points coming into your system, which gives you certain parameters, because if you think about it, in terms of a time prediction or time correlation, at each particular time, I'm doing some action on the website, like adding a item to the cart. Let's say going back, if I see a 30% discount, I go back and see the particular details as to what has changed. So all of these give me a list of actions which I'm undergoing in a series of time steps. And these all can be put in a data store because all of these is being captured. With this, what we can do is we can train a machine learning model to predict what is the next action the customer can do, going into the time prediction domain in particular. If you think about this, we have millions of customers. So for each customer, we might be maintaining another model. So to keep it very personalized. So one model for each customer on a 1:1 ratio. The second aspect is very similar to the Formula One example. We always do not have all the data about the customer because first is they might not be on the website always. Second is we need a lot of data for this in order to train it because for each customer, if you're starting right now, because there are two challenges here. One is if you're an established company, you already have a very historical data of your customer. You're well placed there. But second, let's say if you're a startup or a medium-sized company and you're starting in the e-commerce domain, you need a lot of data to have a personalized experience for them. That is where simulated data comes in. So simulated data or synthetic data is about how do you simulate the customer behavior. So if you think about, we'll touch base upon some of these synthetic data. But again, coming here, how many of you have an idea on the synthetic data before I go ahead? Okay. So to give an idea on synthetic data, what it represents is if you think about a series of events which a customer has gone, let's say from, let's take the F1 race example. So when you start an engine, you have the speed, accelerometer, every other event which you're collecting. That is more from a physical perspective, so you have to burn a lot of fuel and time to collect those data. How about you represent a digital version of it? Because when you start an engine, you already have some physical formulas which can give you these parameters as to at this particular acceleration, what is the fuel you're burning. So this gives you some level of data which can already use. So this is what we call synthetic data. Synthetic data can be generated by machine learning models based on your contextual data. Second, it can be generated by physical models, like for example, the physics of the ground reality, so when a F1 car is running. I hope this gives some idea on what synthetic data represents. Before I go ahead, how many of you have heard about SimPy? Okay, so SimPy is a Python-based simulation framework. I'll give you a very simple example here. If you see here, this is an example of a shopper. If you see, this is a class called shopper. And here we are writing a method called checkout. What checkout does it says that the customer has arrived now. It is spending we can give a sleep here to wait something. So the customer has spent some time in the shop. And then we say that they checked out at this particular time. So this is what a shopper does when they come to a shop. And if you see here, this source class generates a random number of shoppers here through a for loop here. So basically it's saying activate this shopper and create a checkout for each of them. So very simple process, you're generating 10 customers. For each customer, you're saying visit the shop and check out. If you think about this, the checkout process, what it does is, when you are at a checkout counter, you always have a period of time. Let's say from your experience on a retail shop or in a store, when you go, you always spend some 10-15 minutes, right, before you check out, or you can say 5 minutes before your checkout is processed, money is transferred and everything, right, from a simple perspective. So if you think about this, 10 customers spending 5 minutes each, it takes around 50 minutes. So it kind of simulates this behavior of your shop, of your process. It could be anything. It could be a car shop, kind of a factory process. Now, if you think about this, I can use a PySim environment to generate some of this data for my retail shop. So I can fix some of this data, like as a customer, they visit at this time, they spend some time at this particular location, and then they spend in the checkout time. So I get some behavioral data here. For this could represent some synthetic data for me. There are various ways to generate synthetic data. This is just one of them, which is very simple enough to start with. Now, this is a very simple setup which I can start with. I can set up a SimPy environment in an EC2 compute. What I can do is I can just very statically say 10 customers, loop through it, and visit web page, checkout, and cart. So I can have a very series of actions here. One challenge here is it's very static. I'm starting with 10 customers, and it doesn't give me any value because only I know what I'm setting here. There's no dynamism here, but good to start with, at least to have a fundamentals here. The second part here is I can set my configuration in a DynamoDB. So instead of setting it in the SimPy in EC2, I can get the configuration set by some other manager of the store who says that customers come and they spend this many time and this. So they set the dynamism of the numbers. But if you think about it, it's also still static. We are getting some reference from a single person. So it's simple, it's static and not dynamic. It's not scalable because you're running everything on a single compute. And the fourth part is that it's disconnected from reality. The next part is the configuration or model driven. If you think about previously, if for each customer, if we have a one machine learning model set up on a 1:1 ratio, so for each customer, we have a model. Now, we all had a reference to the customer logic where the customer was created, right? Which was doing the activation or the checkout. So here, what we are driving here is, we know the configuration as to what a store consists of. Let's say a store consists of checkout, cart, and various other steps here. But how a person reacts to each of this is governed by the machine learning model. So there is a bit of dynamism here because it's not now correlated. It's a dynamic and it gets all these feedback from the machine learning model. So this architecture now is complex. One of the side effects is the architecture is complex. It is not maintainable because for 10 customers it's good, but if you have a million customers, you don't want to maintain million models. It's highly cost and it's dynamic. Scalability, you can think about ways to scale this up using different other tools. So it's possible to scale it up. It's not entirely disconnected from reality because you still have some customer behavior from the historical data, which is represented through your models, right? They're governing it. Now, if you think about this particular scenario here, so you have the customer who interacts with the system. These events are now collected in some database. That is the real-time events which are happening. And at the same time, you have the twin model below. So twin model is a digital representation of it. The same events are also being trained because your model needs to know what your actual customer is doing or the real version of it is doing so that it's very similar. So it doesn't drift from what the customer is actually doing. The third part, if you see, is actually this twin model is given a sandbox environment where they can interact with it, very similar to the customer. So now you have two entities interacting with the system, but in two different environments. This gives you an idea about how these two entities are interacting separately, giving you if they're drifting away. If they drift away, you have a feedback loop at the end, which gives you that the model needs to be further trained to have the generalization capability of it. I hope this is clear to everyone, this picture. So if retrospectively, if we think about this, maintaining models is a very skilled task. You need machine learning skill for that. There's a cost, time, and real-time synergy needed with the practicality of it. If you have 1 million or more customers, which is the reality for every organization, you cannot do this. And it's not very agile enough because your customers' data will change very quickly. You do not have time to train your machine learning model and to react to them in real time. So this does not align with it. This is where OpenSearch comes up. In terms of its capabilities, particularly here we are trying to focus on vector search. Here, the idea is, could we leverage generalization instead of being very focused on creating machine learning models? And I hope everyone knows about what RAG architecture is. So this is a very general representation of it. If you think about this, you have customers who visit your checkout, web page, and cart, and these all events are captured through different, and for each of your organization, the systems could differ, but there's a basic process. You capture the events on the real time, you feed it through some system and store it. Here it is S3. What happens here is for each customer, you also have some data, right? Like they logged in and you have some name, email address, and some information. And you have a very changing dimension called events. So each customer has different events happening for them. There's a pseudonymized layer here. What it does is it pseudonymizes your data. When you talk about pseudonymization is that you have customer number, you have email address, names, which are more PII data. So if you want to convert them to a form which cannot be reverted back, many organizations do it in different ways. You can revert it back, or it's a one-way hash, so different ways to do it. But let's say it's anonymized, and this is where the second step happens is Lambda now collects any new event which happens in S3. Lambda is invoked, and this data is now stored in OpenSearch in a vectorized format. It's a very similar format in here too, but the difference is that there's a twin model here. So the twin model is also playing at the same time in a different environment. And the data is also captured in OpenSearch. Now, this is, if you see, the parallelized layer, which at the same time the real customer is interacting, and the twin model, which has been kind of trained based on the real customer, is also playing at the same time. And here it is a PySim model, and it's not actually a machine learning model here. Now, if you think about here, we had the top 3 layers previously. Now, the second layer which happens is, if you see the digital twin, the events which are generated by it can be used in different setups. Now you see there are 2 layers at the bottom which are doing a RAG call. So what they're doing is, whenever a new S3 event is generated, you're calling a Lambda expression. So one use case for it is, let's say a customer has visited your page where let's say they want to buy a sneakers, and you know that they have visited it 2 and 3 times. So it's a custom logic you want to write. So because if you're seeing they're very interested, they're coming back, but there is a bit of a friction in terms of their getting to the checkout. So here what it does is, let's say you want to react to them in the real time. So what you want to do is, you captured the event from S3, you saw that this logic is represented in your Lambda experiment here, and you can have many such experiments parallelly because each of these Lambdas are subscribed to the S3 event, so they can run parallelly. Now with this approach, what you're doing next is, from OpenSearch you're searching what is the different time-based approaches it has taken. Because when you think about large language models, I'll come to this point, but now what it does is it gets the context. It now suggests, based on this, we can recommend some percentage of discount, because that will be in the prompt in the large language model. So based on the particular expect and the cost, we want to give them a particular discount. At this point, what the system does is it either sends them an email, which you see it's going to the SES service and sends it to the customer. They're just a very simple flow. You can also do a pop-up and different ways. They're just a starting element. You can change it in different ways. And if you see the flexibility of it, at the same time, you can run multiple parallel processes. Now, here, if you see, this gives you a chance to experiment in a very sandboxed environment without experimenting with real customers. The real chance comes when you try to verify it on a real customer, because when you do that, based on the probabilities of it, you'll get a feedback whether the customer actually brought it. And this is where eventually, over a series of time, your actual customer and the twin model will converge. You'll initially see a divergence in terms of the behavior because you don't have all the data in terms of how your machine learning or the LLM model's response tuned with the response of the customer. So there's always a bit of randomization, but that eventually gets converged in the long run when you start with it. If we all know about semantic embedding, that's how we know about RAG in particular. So you have a context and you have many other subcontexts. And whenever you search, it gets re-ranked. Let's say context 1, then context 2. So you kind of use it. But are contexts that helpful? Because if you think in this particular aspect, what am I putting into the context? A series of events which are time-based. But these contexts are not much helpful. What should I search upon? Because a large language model is expecting to know a pattern of time series events. It doesn't understand very particularly a single context. It needs a whole context. Right? And these contexts could be how you chunk strategies, right? So contexts are very helpful, but there is a catch here. We have all heard about how you do chunking strategies. So you chunk based on some overlap, or you summarize. There are different ways to it. But I like to think about it in two different aspects here, particularly groups, orders, and summaries, which could be horizontal, and vertical, which means textual, meaning, or temporal. When you think about a vertical layer, what we usually do is we do textual context matching. So we do a kind of the embedding of the textual and we match it. But there is also the temporal value, which I'll go into the next slides. So if you see here, there is a customer and they have a series of events which are happening, event 1, event 2, event 3. I can store them in OpenSearch, but all of these are very separate, disjointed. If you go a bit on the right side, you see there is a group based on week. So what I'm now doing is I'm collecting all these events together. Whichever is all weeks together, I'm collecting them together, and then I'm storing them. There's another based on a monthly basis. So eventually what happens is this all depends on your strategy. As an organization, if you want to target your customers on a weekly basis as to what they're doing, you need weekly data patterns. If you're doing on a monthly, you'll need monthly patterns. So this is where the flexibility of the system comes here. You're not just relying on the events here, but you're going a step further. You're collecting and you're doing more, if you think this is more kind of subgrouping strategies in the context. And if you see at the bottom, it's written, it's use case based. And the second, it could be summarized too. So let's say you have a lot of events and you want to summarize aspect of it. That too is another possibility here. And the third aspect is grouped. I'm just taking an example here in terms of temporal values. You could adapt it to different other layers too. So here, it's just a grouping in terms of showing you how it's differentiated, starting from the very discrete events to group-based on weeks. And from those, you can also go into persona-based grouping. So let's say you're collecting grouped events for a particular customer, but let's say you want on a persona, let's say you want to target basically on kids shopping. So that is again spread across customers. What you want is a grouped, averaged reaction of customers over that period. This changes given on holidays, different patterns, so that gives you another estimation of it. So model to data modularity. If you saw about this, we started with the models, multiple models, one model for each customer, but we also went to data modularity. We chunked the data, we grouped it in different strategies which are helpful to us. The next part is, since we have the data diversity, this allows us to use different models. So let's say your use case is not, if you take an example of the very basic textual contextualization, that is where you'll use models like, let's say Bedrock, GPT, any others. But let's say if your use case is more time-based, which we focused on this example, you can quickly switch your large language model to one of the ones which are time-focused. So Bedrock provides you with Kronos, you have Nixla. These are very focused and trained on time parameters. So when you give them a series of time events with textual elements, they can predict it very efficiently for you, even with a small amount of data, because they have been trained on a large amount of temporal data, to be specific. So if we think about this, it strives towards better personalization and higher engagement. And if you think about it, you can train machine learning models, but that there is a cost aspect to it. Here, basically dividing the data into chunks and strategies, we're reducing the cost across parallelizations, and you're only getting the cost for the number of requests you're making to the large language model for the customers you want to specifically target to. So you're having a very cost benefit ratio here. And you have faster testing of strategies with digital twins, because once you have a very good parallelized, because first is you're starting with the approximation towards targeting them, giving them value based on their interaction, because the value you're getting is out of the large language models training on huge temporal data set. But once you have more data about your customers, your digital twin and the real customer converge at one point. And this gives you advantage to more experiment in a separate environment. The third is reduced compliance risk, because this gives you, you're not playing with actual data, you have the data anonymized or pseudonymized in one particular aspect. And you can go to another aspect where you're thinking about personas, right? Personas are not very particular linked to one customer, but they target a group of customers. And it depends on whom you're trying to, what your strategy is, whether it's personalization at a very individual level or personalization at a group level. So these are the key takeaways. So PySim is only one way to emulate your data. There are different other ways. You can use a machine learning model. There are other simulation frameworks too. It gets you quickly started with. We just took an example of events. So PySim can eventually generate these events too for you. The second part is, let's say you have a factory environment where you have manufacturing processes going on. So one, let's say an aircraft part being generated process. So it goes through different flows in the process. So you know what time it takes. If there is another expect happening at different time, you know how it affects your system. So you get some data from a pre-setup environment. So that is how this helps you in. And OpenSearch, if you think about it, helps you with real-time analysis by getting those. And if you think about it, it's all about your strategy in terms of how you're chunking, grouping. And if you think about it, it really lowers your cost down, because you're more playing in the CPU in terms of the chunking and everything. And you get very fast results. So if it doesn't work, you can try a different strategy. And at the same time, you can chunk your data in different layers. And one particular aspect, if you think about, is this is very helpful because you started from a very top discrete level, and now you're grouping. So you're reusing the data instead of just playing with different set of data. The general idea about going with personalization is to use machine learning models which are very specific to a user. There are also, if you think about ensemble models or XGBoost models, they also help you in terms of connecting all this data together through a single model. But again, the cost comes in terms of cross leakage of data because it could happen. So RAG plus LLMs really help you very quickly to personalize your campaigns or personalize the experience of customers. And at the same time, they're very compliant in terms of how you're starting with it. So this is a very short introduction about myself and the books which I've written. There's a short 20% discount code for all OpenSearch Con North American attendees. Okay. Any questions for me? So if you think about that, one particular part is let's think about you're not targeting customers. So I think that's more. I think you're not taking any action. So I think some action is better than in no action. That's because I think you're disengaging with the customers. Second is keeping the customer engaged. It gives you some, I think, leverage because you don't have your customer data in terms of when you're starting with it. But at the same time, machine learning models, particularly I think the Bayesian models, they help you with the randomization aspect of it. And I think the random aspect, it plays into the A/B testing part here. So eventually what we have been doing in the past is we make a change to a website, let's say for example, and we want to know if customer will have a very good experience with that. So what we do is we say 5% users can use that and 95% target the other website. And you get feedback that way, right? So that is one way to approach it. The third way is what Bayesian networks have taught us is that even that is not much helpful because the randomization thoughts in terms of how human beings are. So that also helps you a bit in terms of starting from a Bayesian model. That helps you to give that randomization a thought because I think that gives you some leverage, at least in terms of experimentation. The fourth part I would say is there's a lot of data available in terms of what range of users they fall into, because it's eventually I'm talking about different other aspects because if you're starting new, you need to capture your data, but you also need to leverage other data. So what some teams I've seen doing is that they capture Twitter data. So they know particular customer, they go and see what they are doing, and it goes into how you track about them. But eventually you have to be compliant also at the same time in terms of how you leverage. So there's a balance you have to go there in terms of how you approach it. Because some companies have done that, but I think there's a legality in terms of how you can track and get the data. And the third aspect is the generality of it. So when you see that a particular group range, age, a particular, based on the gender, so there are some expectations in terms of how they react to particular category. So that gives you some leverage, I would say, but not definitely. So if you think about those aspects, you can take some small actions in those directions, but those are, I wouldn't say those are very particularly helpful to you. So I'd say at this particular movement, this is more of a. But this is I think you might not have heard about this in very particular in terms of LLMs in particular, and the grouping aspect of it. So this is more kind of a very novel approach, I would say, in terms of how you're grouping this. But if you see, this is more about how you train your machine learning models on a weekly basis. But how do you send this on a weekly to a trained model? That also helps you here. Now, could you repeat your first question? So I think simulation is a very important part, and it really helps you. The first aspect I can go back to the example of what these two particular industries are doing. If you think about Formula One racing, they don't have real data So they don't, every time they don't want to run the machine in particular. One could argue that they are using a lot of historical data, but if you think about this in particular, they might have historical data, and some of these data are very eagerly shared among teams too, so that they can improve in general. But they are using simulation here. When you think about simulation, they are using about the dynamics of the engines which are operating in terms of the acceleration. So that if you think about the physics-based models, they already know about when in this particular temperature, in this particular environment, this is what you will expect the engine to behave in. Now you do not have the temperature and all those details, but you have the weather details for that particular terrain somewhere, because these are weather details. Those can help you to drive some other insights here in terms, because those are some inputs to your model. In this particular temperature, in this particular terrain, how would my engine respond to? So there are different coefficients you can define here. If you think about simulation is generating a lot of data for you here. And based on the simulation, you can also train machine learning models if you don't have very huge data set. Okay. Okay. Any other question, guys? Okay. Thank you so much for your time today. Have a nice day.